Welcome to the optical communication course. Now today we will learn that it is dispersion. As we have mentioned that there are the signal distortions occur in the optical fiber because of the loss inside the fiber, and that loss, that we say it is nothing but a attenuation, and that attenuation is depending upon that length of the fiber. Second theory, we say that because of that fiber, we bend the fiber. Because of that, there will be a bending loss, or because of that curvature, there will be a curve loss. Because of that curvature of a fiber, there will be loss occur. That is called as the bending loss, or we can say that because of that curve, there will be loss, and that loss belongs to the bending loss. So in that bending losses, we have seen that micro bending and a macro bending losses, and along with that, we have seen the other losses because of the process manufacturing process. That fiber is not able to work at that particular operating wavelength. So that losses is nothing but scattering losses, means up to particular threshold voltage, threshold power, that losses occurs. So that ray will not propagating through the fiber. So that's why it is called as a scattering losses. And then the losses due to the material. So we can say that intrinsic loss and extrinsic losses. Okay, so that is about your fiber. So we have seen that intrinsic absorption or extrinsic absorption. That is nothing but a losses due to the intrinsic absorption and extrinsic absorption that we have seen. Now the next type of a distortion is nothing but a signal distortion, and that signal distortion occur for a given particular signal we are transmitting, and that signal get distorted at the receiver here. The signal we are transmitting, that may be an analog signal or a digital signal from the given particular source. We say it will be a laser source, or we can say that it will be a LED source there. Here, a conversion of a signal takes place, whether it is analog or digital signal, in the form of a current pulse, and that we are transmitting through the fiber, and then that same current pulse is to be received here. So in the case of a dispersion mechanism, what happen? Whichever the pulse we are transmitting, that is current pulse, we are expecting the same current pulse at a receiver, but due to the dispersion, pulse get broadened. Okay, now this width of the pulse is increases, means that is broadening of the pulse takes place. So that's why we are not able to recognize whether that pulse is having information of a 1 and 0 in a digital form. Means generally what here at the source, whichever the informations we are having, that is 1 or 0, that will be converted into a current pulse, and then current is converted here, current pulse converted here in the form of a light. Then light is traveling along the fiber, and then light will be received at here, and then conversion takes place, and we'll get that current, same current pulse. Since the length of the fiber is large, so that the broadening of pulse will be large. So if you consider that we have the signal, and that we say that there is a pulses of a signal, we say here it is about 1, then this will be a 0 here, then another pulse is about 1, and next pulse is about a 1 here. I mean, this belongs to a 0. These are the pulses 1011 here, and this is nothing but the amplitude of your pulse. It is constant now for the given pulse. It is a constant because I just draw here. Okay, so this is about your amplitude of your signal. It is a throughout constant. But when we transmit the pulse, that is about amplitude A here, and we are receiving the pulse, that is value of A. But this, what happened here? For a given particular distance, when we are receiving the pulse, that pulse gets broadened here, and that amplitude reduces. So then we are receiving the pulse with some particular distances. Here, if you see that this one is 1, this one is 0, this one is 1 and 1. So this 1 and this 1, if you see that, it looks like a merge here. That pulse is not able to distinguishable here with a 1 here. But again, if you further increase the length, okay, if that length of the fiber is long there, in that case, we are receiving the 1 and this amplitude reduces. Here we say that it's about amplitude reduces. Then 1 is here, but 0 it is overlapping with respect to the another pulse, that is 1 and this one. And then 1 and 1, if you see that, it is combinedly that amplitude. If you measure at that particular period of a time, so it looks like a 1. But this 1 belongs to which particular pulse is not recognizable here. Or in another way, if you say that these are the two current pulses are transmitting, and then at a particular length of the fiber, this broadening takes place, and then these pulses are received likewise. Means we can say that this pulse is 1, but it get broadened. It is again here, it get broadened. And then this particular portion is nothing but intersymbol interference here. We are not able to identify that 1 here. This 1 belongs to, or that pi value is belongs to which information is not able to identify. Or you can say that these are the non-distinguishable pulse because of that overlapping here. Okay, so because of that overlapping, we are not able to distinguish the information. So that is called as a intersymbol interference. That is called as a intersymbol interference. That is ISI. Now we say that this interference because that pulses are overlapped here. So due to the broadening of pulse, that pulses overlap. So then we are not able to recognize or identify that what light pulse or what current pulses are transmitted to the fiber. If the length is increases further, then they will be further again overlap and they broaden. So that's why we are not able to identify that 1 and 0. Because of that length of the fiber, each pulse broadens and they overlap with its neighbor pulse. So that's why they are not able to, we are not able to distinguish these pulses. Means what? At the receiver, that overlapping of pulses is not able to distinguish here at the receiver side. So that's why it is called as a intersymbol interference. Because if you say that in a fiber, we are sending not only a two pulses or single pulses, we are sending a large number of pulses, and then at a receiver, because of that pulse broadening, that pulses are not able to distinguish here. Then at the receiver, there will be large error, or we can say that a signal to noise ratio. Okay, signal to noise ratio at the receiver, that will be changes there. Okay, means decrease now. That signal to noise ratio reduced, and you can say that a distortions at the receiver because of that overlapping pulses. So the operating bandwidth of a given particular pulse, particular communication will hamper here. So means they have the limitations for the respective bandwidth. So if there are the no overlapping of pulses in a optical fiber link, then generally we consider that bit rate, okay, because of a no overlapping, because of a no overlapping, we generally consider that bit rate is depending upon only the pulse duration. That is about a bit rate. Here we consider that non-overlapping of a pulses that propagating through the fiber, and because of that, because of we can say that pulse, we say that a broaden through the dispersion, and that limits the bandwidth, or that limits the bit rate. So bit rate is nothing but what 1 by twice t. And if you consider the pulse output is of a Gaussian shape, so in that case, our bit rate becomes what? Or we can say that is about a maximum bit rate occur, that will be is equal to the zero point 0.2 by, that is a shape of that particular Gaussian pulse, that is nothing but a sigma, or we can say that a RMS width of this particular pulse, that will be a sigma here. That is zero point 0.2 by 6. That is about a bit rate here. And if you consider in terms of a bandwidth, so we can relate that bit rate with respect to the bandwidth here. So for that purpose, we should know that what will be the format we are using for sending the pulse. So depending upon that digital format, so bit rate we can calculate, or we can say that we can calculate the bandwidth here. If supposed to be a non-return to zero, if we are using a non-return to zero format, or we can say that a return to zero format. Okay, so in that case, NRZ or RZ. Okay, we can say that NRZ or a here only the RZ here, non-return to zero and return to zero format. So for that, a bandwidth is equal to, or we can say that whatever the bit rate we say, it will offer maximum 1, so it will be of a twice b here. And for the return to 0, that bit will be is equal to b here. So now the return to 0 means what? Is for a given particular pulse of a duration. Okay, that is about a duration we are saying. A complete, that is about a period we say. This is nothing but a complete total period of a signal here. But we say here 1 and 0, that can be recognized if it is a non-return to 0 or a return to 0 pulse. Means a pulse amplitude of that we say 1, or we can say it is a 0, or we can say it is a 1. And this 1 and 1 is, we can say that, distinguishable for the your given particular period. This belongs to 1 and this belongs to 0 here. So similarly, we say that this belongs to 1 here. But in the case of a RZ format, so this particular pulse or particular time period here, it is nothing but that a time period is about it to here, and for the return to 0, that 1 just write likewise this is nothing but a 1, that is about a return to 0. So in that case, your pulse, your signal, or you can say that a relationship between that particular period of a time will be a, so here that will be a 1 and 0, we can distinguish here. So this is about a pulse duration, and this one is about a pulse duration. If you see that total signal, and they are distinguishing just one, they are distinguishing the one here. So in that case, we can find out what will be the optical bandwidth for the given particular pulse is propagating to the signal. That is about the mechanism. So if we are using a single mode fiber, then the dispersion is a small, because the error in the case of that fiber, that error is small. But if you use a multimode fiber, then they have the dispersion. Then according to that, we say single mode and multimode fiber. So what will be the dispersion occurs? Because there will be a waveguide dispersion in a single mode fiber. So we talk about the types of dispersion depending upon that how many number of modes are propagating through the fiber. So that's why they have the two types of a dispersion. That is, we can say that the intramodal dispersion, and second is about the intermodal dispersion. So in the case of intramodal dispersion, generally it is occur, that is about a multimode fiber. Even that same can be occur even if we use a single mode strip index fiber. But the dispersion is depending upon the factor of a wavelength, and again it is depending upon that what will be the pulse width. So if we use a single mode fiber, we say that a pulse broadening is minimum. If we use a single mode fiber, they have the minimum pulse broadening. So that's why a single mode fiber, they have the higher transmission bandwidth. Okay, that is, we can say that is about a transmission bandwidth is a higher here. So that's why just say that data rate, because we can say that data rate will be higher. And if you consider that a multimode fiber, in that case, they have the limitations of the bandwidth here. Okay, they have the limitations of the bandwidth, because that multimode fiber, they have the large or greatest dispersion there, large dispersion. And that a dispersion in a single mode fiber and a multimode fiber, if you compare, because pulse broadening is minimum, so that's why the low dispersion. But here the large dispersion because of that pulse broadening will be a larger. And a pulse broadening generally that will be depend upon a factor of length here. That will be depending upon that length of the fiber, or you can say that the distance that pulse travels. Okay, that how long that pulse travels throughout the fiber or within the fiber there. So that's why the pulse broadening they have the restrictions on the bandwidth because the distance increases. Okay, the distance increases, the pulse broadening increases. So that's why that they have the restrictions on the bandwidth. So to avoid it, we need to use the repeater. Okay, to avoid it, that pulse broadening, we need to use the repeater here so that we can minimize the that pulse broadening there. Means pulse broadening effect can be minimized using the repeater there because after that particular distance or particular kilometer of a distance, that this pulse broadening will be large. Pulse broadening large means there may be a intersymbol interference or there may be a dispersion, and because of that, for a given particular length of the fiber, we need to use a repeater, and then we can minimize the pulse broadening. So that another factor is about a if you consider that when we couple the fiber, or we can say that for the given particular length of the fiber, so that pulse broadening will be small or a large. Okay, so that's why we need to know about that how many number of modes are propagating through the fiber there. So generally in a single sentence we say that a pulse broadening increases linearly with the fiber length. So that's why the bandwidth we say that which is inversely proportional to the distance here. Okay, we can say that a pulse broadening is directly related to the length here. Or you can say that linearly. Okay, increasing the pulse broadening linearly increases with the length of the fiber. And so that's why we say that bandwidth is inversely proportional to the distance here because of that pulse broadening there. Now we take a single example here with a multimode fiber and how that pulse broadening takes place and what will be the intermodal dispersion in each particular fiber here. We'll see. Simple example I am going to draw here with a pulse broadening in the gradient index fiber that will be of what we can say a multimode fiber of a step index or multimode fiber of a gradient index and the single mode step index fiber. So for that we should know that what will be the structure or what will be the refractive index structure of this particular fiber here. Now this one is about a step index fiber because it changes abruptly. So this belongs to the step index fiber. We say that this one is about our fiber here. Okay, this one is about you can say a core here, and this belongs to a cladding. And above that we can add a coating that is we can say that is about a coating of the given particular fiber. Now if you consider here the pulse is propagating through the fiber, generally it has a core and signal is propagating to the total reflection. Likewise, the signal get reflected from the fiber. But the output is nothing but that a pulse broadening. This is about your input and this belongs to your output. And this one is about your how your signal is propagating through this. Means how this is about nothing but a ray optics inside the fiber core. But if you consider that in the case of a gradient index fiber, that profile will be a parabolic one. So this is nothing but n of r here. That r is changes gradually. Okay, at the center it is maximum, and then it will be decreases there for the radial distance. Same fiber we see that is about a core here. This one is about a cladding. This is nothing but a fiber. We say it is about a input pulse. And then if you consider the internal structure here, sorry, how your light is propagating through the fiber, because of this particular axis, your signal will be propagating likewise. Okay, it will be propagating because they have the variation in the that particular code. Just like it is just like a signal will be likewise. Okay, if you see that the signal is propagating through the fiber because of that variation in the refractive index, and the output again it will be a pulse broadening here. Okay, same in the step index fiber and same in the gradient index fiber. But if we consider the a single mode fiber, that core is small. Okay, this is about a small here, small core, and the fiber we say it is about a small core. Likewise, I just draw it big one. Okay, it is a small core here, and this is nothing but your optical fiber, and we say that pulse is transmitting. It's like a pulse is transmitting to the fiber. This one is about a core. This is about a cladding here, and we are receiving the pulse. That is about a small broadening takes place. Okay, okay, broadening will be very small for the given length of the fiber. Now, in the case of a multi-mode, broadening will be large, whether we are using a steep index fiber or a gradient index fiber. So this is nothing but what we can say a multi-mode step index fiber. Multi-mode step index. Here pulse broadening takes place. This one is about a multi-mode, a gradient index fiber, and this one is about you can say a step index fiber. That is called as a single mode step index fiber. Only one mode is propagated. So that's why the broadening will be there. And that broadening, as I told you earlier, that pulse broadening is minimum in the single mode fiber and multi-mode fiber, large dispersion. So it pulse broadening will be a maximum here in the multi-mode fiber. So pulse broadening directly affect to the bandwidth because we say that if pulse broadening is depending upon that length of the fiber, so your optical bandwidth we say, or you can say that bandwidth length product is depending upon that bandwidth of optical signal with respect to the length of the fiber is equal to the information capacity. That is about the length of the fiber will tell you what will be the capacity for the information. Or you can say that a channel information. Okay, that is nothing but a bandwidth. So that is called as a bandwidth length product of a given particular fiber, and that will give us the operating, what will be the total channel capacity, and that is depending upon that length of the fiber. So all the factors are depending upon that length of the fiber. Next we consider here it one by one a dispersion. Now we talk about first intramodal dispersion, and that intramodal dispersion is nothing but operating, or generally people are saying for the intramodal dispersion, some books they have said that a chromatic dispersion for the intramodal dispersion. And that particular intramodal dispersion occur in all types of optical fiber, and that dispersion occur because of that a spectral width, because of the spectral width of a optical source, that in that dispersion occur because of the spectral width of the optical source. Now what do you mean by spectral width? Generally we say that whether our source it will be a LED or whether it will be a laser one. So this produces a radiation of the signal, even the same to the laser, or it is about a coherent or a non-coherent source, as we say. So for this, what will be the optical sources we are using, and they emit the light, and that light doesn't have the same frequency, single frequency. Whichever the source we are using, they doesn't have a single frequency. Okay, they doesn't have the optical sources. They doesn't have a single frequency. Means they have the band of frequencies, or we can say that that is for a given particular source. They are working with a different frequencies there, and that range of the frequencies start from the F1 to Fn, and that is nothing but the spectral width of your particular source here. Suppose I am saying that this is about F1 frequency, F2 frequency, F3 frequency, likewise to the Fn now. So they are nothing but a different spectrum, or I just draw here the different frequency signal now. Okay, likewise, I just draw here. So that is about a source doesn't have a single frequency. So they have some particular spectral width, and because of that spectral width, so they have the different frequencies here, and that different frequencies signal reach to the other end with a different delay, means propagation delay. Okay, again there will be a propagation delay, and that propagation delay difference with a different spectral components occur when we transmit a signal there, and at the end if you see that that velocity is depending upon the frequency here, or we can say that is about a wavelength. Instead of frequency component, you can say that is about a L1, lambda 1, lambda 2 also. That is depending upon the velocity is depending upon that each of the signal or each of the frequency transmitted through the fiber there. So because of that propagation delay, or because of that difference in that particular transmitted signal here, because of that various spectral components, okay, so that pulse broadening occur. So, and that is called as a, we can say that is about a dispersion. So we can say that a pulse broadening of each and every transported mode, okay, they have the dispersion, each transmitted mode, they have the dispersion. So each mode they have the dispersion. So that's why that is called as a intramodal dispersion. And a delay differences that will be caused by the dispersive properties of a waveguide material used. So that's why it is called as a material dispersion. And a fiber guiding your signal. So that's why it is called as a waveguide dispersion. So for each mode, intramodal dispersion. For the propagation delay differences, it is called as a material dispersion or waveguide dispersion there, waveguide material dispersion. Or you can say that a guiding your signal guidance effect within the structure, that is called as a waveguide dispersion. So in the case of a material dispersion, it is depending upon that, or we can say that pulse broadening due to the material dispersion because of that various spectral components. Various spectral components of what? A optical source have the various spectral component. And because of that various spectral component, that optical source has the different group velocities. Okay, that optical source have the different group velocity. So group velocity is depending upon that same operating frequency signal. They form the group and they are propagating through the fiber. So that is called the group velocity. Now because of the different group velocity, because various components are various spectral components are there, they have the different group velocity. And the same signal is launched inside the fiber. So that's why that will propagating through the fiber. So that will generate the, that will create the dispersion or signal distortion. Why this occur? Because of that signal have the different phase velocities. Okay, this have the different phase velocities, and that have the different wavelength. So means we say that here a signal propagating, they have the band of a frequency. Just I told you that is F1 to Fn. Likewise for the given spectral component, and they have this a propagation delay as I told you earlier, and that will causing the pulse broadening inside the fiber. So phase velocity of the given particular wave propagating through the fiber, that we say that depending upon the wavelength. So that's why we can say that the wavelength is depending upon the dielectric medium. So that's why it is called as a material dispersion there. And another factor is about your light is propagating through it. They have the signal propagating through the fiber, it is depending upon the refractive index. That light is propagating through the fiber, and that velocity is depending upon that refractive index of the fiber. And if that refractive index of the fiber it changes with respect to the wavelength, then the dispersion occurs. So pulse spread or pulse broadening, it is depending upon that a group velocity, or you can say that it is depending upon that group delay. So we will calculate that a group velocity that will be depending upon that d omega by d beta here. As we know earlier, that group delay is depending upon that what will be the changes with respect to phase and with respect to the omega here. And that refractive index constant, we say that it is generally, it should not be a zero, non-zero value. Means we can say that d square n divided by d lambda square is not equal to 0. Then if you solve it for the group delay, and that will with respect to, because we say that it is depending upon that velocity. So n1 minus lambda, that is dn1 by d lambda, and that is but a group delay. And here a n1 is nothing but a refractive index of a given material. So pulse delay due to the material dispersion in a fiber for a given particular length is depending upon that the length of the fiber and n1 minus lambda will write directly here with respect to that d lambda. So this one is about a material dispersion and this one is about a delay. So we can calculate that a pulse broadening factor using this material dispersion. So for that purpose, we should know that what will be the spectral width of a source, and a pulse broadening due to the material dispersion that can be expressed in terms of a material dispersion with respect to the wavelength. So I'm just rewriting here the equation. You just see that material dispersion equation. Okay. Now a material dispersion is equal to that is about a spectral width. Sigma lambda is nothing but the spectral width of a source into we have the material dispersion with respect to that whatever the wavelength. So this is nothing but we can say a spectral width of source, and this belongs to the material dispersion. Sorry, this is nothing but a pulse delay due to the material dispersion. That is a pulse delay due to material dispersion. And this is nothing but what we say it is about a material dispersion. So using this equation of a dispersion here, we can calculate that a material dispersion, that is L into lambda by C dn1 by d lambda minus d square n1 by d lambda square minus dn1 by d lambda. And after solving this, we'll get that L into lambda by C d square n1 by d lambda square. So approximately we can calculate that a material dispersion is equal to sigma lambda into L divided by C. And this one is the important modal factor mod d square n1 by d lambda square. That is about a